Hello, parents and any teachers who may be watching. Welcome to Creating Math-Ahas for Parents. I'm Dr. Sandy Atkins, Sandy, and in this video, we're going to look at multiplication. We'll look at some of the models and the meanings of multiplication, how that links us to the language that will help your children have the imagery for multiplication, and then link that to algebraic properties. Now, if you find this video useful, I hope that you will like it, give it a thumbs up, share it, subscribe to the video. It really will help. Subscribe to the channel, and then you'll hit the notifications bell so that you know when other videos are coming. Now, in terms of meanings of multiplication, we have an equal grouping model where children learn about combining equal groups. We have an array model where we're looking at combining equal rows. We have a distance model where we're combining equal jumps. And then we also have an area model. And when you look at 3 times 5, that's how I would have primarily read it. 3 times 5, perfectly correct. Nothing wrong with that. The challenge is that language is not in story problems most of the time, right? There is language like groups of, 3 groups of 5, 3 rows of 5, 3 jumps of 5, a rectangle that's 3 by 5. See, these models give us that language, and I use that language when I see the symbols. So I'm developing the language of story problems all along. Now, your children will hear the word times in a story problem, perhaps, when they get to multiplicative comparison, 3 times as many as 5. But these other models bring with them strong imagery and again will lead to algebraic properties. Now, one model you may see will be this for an equal grouping model. But before we jump into that, I want to look at some organizing models also. The one on the left would be a 5 frame, the one on the right, a 10 frame. If you look at 5 in each of these frames, quite often we think of that 5 frame as the one you use up to the number 5, and then you get them into the 10 frame for numbers greater than 5. But you see, nothing says that 7 can only be shown in a 10 frame. When it is a 10 frame, I'm looking at 7 in relation to 10, typically, 3 fewer. But if I do 7 with the 5 frame, I see that 7 is 2 more than 5. I'm thinking of 7 as 5 and 2. Now, when I want to double it, see, look at the top image versus the bottom image. Double 7. To me, that top image is a cleaner image. I'm not having to ignore some of those squares. I can see it as double 5. That gives me the 10 put together with double 2. See, that's also the imagery of the distributive property. So I can use that distributive property imagery to do 3 7s, 3 5s put together with 3 2s. Now, let's organize it into the equal grouping chart. Do you see how I haven't just thrown those little cubes in them randomly? Because I don't want your child to have to repeatedly count. See, by organizing it in some way, I start to see those clusters, 3 5s put together with 3 2s. Typically with the equal grouping chart, we would slide everything down into that larger section. And again, you can see the 3 5s and the 3 2s. So this is your distributive property. What is 3 7s? It's 3 5s put together with 3 2s. How did I think of 7? As 5 and 2. Now, nothing says I have to think of as 5 and 2. I could have thought of it as 4 and 3. What do I have? I have 3 4s put together with 3 3s. Thinking of 7 as 4 and 3. Distributive property again. Okay? Now, once I have that idea strong in my mind, it's not a big jump to go to 3 23s. These are base 10 materials, so you can see the rods of 10. How do I make 3 23s? Well, I think of 23 as 2 10s and 3 1s, 20 and 3. What do I have? I have 3 20s put together with 3 3s. And it's not a big jump then to get to 3-digit. What do I have? I have 3 hundreds. There's my 100 model, 3 20s, and 3 3s. Distributive property. See, once your child understands that I can take a number and break it up, like 3 7s, and think of 7 in many different ways, I use that same idea and place value to do 3 groups of 24 and 3 groups of 123. See, as long as I'm using that single digit, I can actually multiply up towards a 4-digit number, and it's not going to be a huge leap because I understand what is going on. And it's also manageable for the pictures I might draw. Now, if it works for whole numbers, it works for mixed numbers. See, what do I have? I have 3 groups of 2 3/4. I can use this equal grouping chart again, and this would be a fraction kit model where we make fraction kits with your child. They might use construction paper. Notice how I'm not labeling my pieces. That's purposeful because I want them to go back and have that embedded practice of knowing why I would call that green piece a 1/4 piece. If they're labeled, it's a reading activity, so it's purposeful. As with all the materials we use, it's purposeful in what we're using and how we're using them. Now, nothing says I have to use the equal grouping chart. I just want 3 groups of 2 3/4. I'm thinking of 2 3/4 as 2 put together with 3 1/4 pieces. So I'm going to have 3 2s put together with 3 3/4 pieces. And to figure out my total, see, I can think of sliding those 1/4 pieces from the last group in to complete the holes in the first 2 groups. So what do I have? I have 3 2s put together with 3 3/4. What do I have? I have 6 put together with 2 1/4. Okay, 8 1/4. Now, here's your array model. I can do the same thing. I can think of these 3 rows of 7 for 3 times 7 and cut them, slice them. So I have 3 5s put together with 3 2s. I can do the same idea with the area model. Now, think of the language. I'm talking about dimensions of a rectangle. But for many of you, your 3rd grader will be learning about area. And I've had a lot of children tell me over the years, well, one thing you need to know, only one thing about area is length times width. And then they're shown something like this. See, what I need them to understand is I can cut this apart. I see that 2 by 3 rectangle and a 2 by 2 rectangle. Some children see a 2 by 2, a 4 by 1, and a 2 by 1. Nothing wrong with that. But what I need them to understand is when you find area of a shape, I can cut it into smaller pieces, find those individual areas, and combine them to get the total area. Area is additive. Now, this length times width idea, what about this? See, length times width doesn't work for a circle. What we do want to understand is it's a square unit measure. It's a 2-dimensional measure. So we're going to measure area in square units, but we want to move them from seeing all of the squares as we've done here and cutting it as we've done in the previous ones to seeing the outline of the rectangle and visualizing the individual squares, but not actually having to draw them or see them. So I can do the same idea here. I can still think of 7 as 5 and 2 and make a cut, find the area of the 3 by 5, find the area of the 3 by 2. My total will still be 21. Now, some of you may be thinking, my child already knows 3 times 7 is 21. Why are they spending all this time on this? See, knowing that fact is great, but we're building the imagery of the distributive property. We're going to use the language of the commutative property to also help us when we get to mixed number multiplication. But this foundation, see, knowing that fact doesn't get me to the distributive property. These images do. Now, 3 by 27, how can I think of 27? 20 and 7, make a slice, find the area of those 2 sections, add it together. It's my distributive property again, right? So I've got 3 20s, a 3 by 20, and a 3 by 7. That was monomial by binomial, the way it was written, right? 2 terms, 1 term times 2 terms. Here, I'm technically doing binomial multiplication, a 2-digit by a 2-digit. See, I can think of it as 54 by 33. How do I want to think of 54? 50 and 4. 33 is 30 and 3. I'm going to make some cuts to this. so that I'm going to find the area of each of those sections. And once I find that area, I get the total. Now, for many of your children, we may think that 50 times 30 is a hard thing to multiply. But if they do know their facts, 5 times 3 is 15, then 50 times 30 is 1,500. I know I use a known fact to find those multiplication of decade numbers, right? What do I have? 50 by 30 is 1,500. 50 by 3 is the 150. 4 by 30, 120. 4 by 3, 12. There's your distributive property expansion. Now, some of your children may be learning partial products, and they might not see this area model linked to partial products, but they may be writing something like this on the right. See, those partial products end up matching what's in the area model, whether they'll make a direct link right away, or if they're just using a place value approach, 50 by 30, 50 by 3, 4 by 30, 4 by 3. Now notice how I'm talking about 50 by 30, not 5 times 3. So I'm preserving place value. And if you notice, I went left to right. I went with the 50 and the 30, similar to that distributive property. Some of you may have learned FOIL as a mnemonic. Only works for binomial multiplication, but you might have done that first is the 50 and the 30. And you see those partial products here. I could have started on the right. I could have done the 3 by 4 or 4 by 3, 4 by 30, 50 by 3, 50 by 30. Preserving place value, partial products, and I hope you can see them within our area model. Now, what you will also see me do with your children is I show them those partial products, and then I show them the traditional algorithm. Notice what I've done, right? We've got the 4 times 3. Some of you, I would have heard carry the 1, but we're rethinking of 12 instead of 12 ones as a 10 and 2 ones. And then we had that 4 30s, right, is 120, and another 10 gives me 130. But you see something like this was the algorithm I learned. We just shifted over. Some will write that 0 in as the placeholder. Whichever way you do it, you end up with the same product. But what I ask the children to do is look at that traditional algorithm that I just did versus the partial products and tell me how they're related. How are they the same and how are they different? And if you look at that traditional algorithm, if you pause and look, see what you see. And then when you come back, think about that traditional algorithm. If you look at the terms 12 and 120, there's your 132. And the next two, 150 and 1500, there's your 1650. See, it's a shorthand way of combining those partial products, single rows, okay? Now, that area model, I kept saying distributive property, I keep saying binomial multiplication. This might look a little closer to binomial multiplication. But see, what do I have? I have a rectangle, x by x, there's your x squared, x by 3, 4 by x, 4 by 3. Combine those, I've got x squared plus 7x plus 12. See, your children, when they get into middle school and some in high school, will be using algebra tiles that look like this. But we're building the foundation for this binomial expansion, right? Binomial multiplication. We're building that foundation back when they're doing double-digit multiplication, single by double-digit multiplication. And because it's a property, it works for mixed numbers. I can think of 3½ as 3 plus 1/2, 5 2/3 is 5 plus 2/3. I make my slices, I find the area of those pieces. But now see, I can think about tripling 3 groups of 2/3, or I can think of what's 2/3 of 3. Well, picture those 3 holes sitting there. What's 2/3 of it? Just 2. What's half of 5? Well, 5 halves are 2½ And what's half of 2/3? Well, it's a 1/3 piece. See, my language helps me do this multiplication versus trying to recall that rule. Now, once I do that, I have the 2½ and the 1/3, and we're going to have to find the same size unit fraction piece, which we would have called common denominators, so we can combine those. They have to be the same size pieces. So my 2 1/2 will become 2 3/6. My 1/3 is equivalent to 2 1/6 pieces. I combine it all together and I get the 19 5/6. Now notice what I did not have to do. I did not have to think of 3 1/2 as 7/2 or 15 2/3 as 17/3. Multiply numerators and denominators, then take it back to a mixed number. I'm actually using distributive property to combine these. Now, all of this is using those models of multiplication. Understanding the models and the purposeful use of those materials gets me the imagery I need for algebraic properties and the language that helps me actually do those computations. If you found this video useful, again, if you would, please like, share it with others, turn on the notifications bell so you know when others are coming available, and thank you so much for watching.